Okay. So last time we introduced the idea of the limit, and we were playing around with it a little bit. And we're going to continue, but I actually wanted to start with something else that I think came up last semester, and I kind of forgot about it, and then based on a few conversations that I had with students about their exam, I remember to bring it up again as another potential kind of issue that you might have when actually, did you?
No.
Okay. Just want to make sure. You guys are very close. I kind of want to illustrate my points here by looking over one of the sample finals that you can see on Blackboard. Okay, so this is final exam B. Don't want to spend too much time on this, so hopefully from the few examples I'm going to give you can get the idea of what I'm trying to say. Okay, so this is final exam B, one of the sample finals. If you scroll down to problem 7. Problem 7 is what I want to focus on at the moment. First thing, anything you notice about problem 7? Anything that jumps out at you? It was on the test. There was a problem exactly like this on the test. I literally went to this problem and I changed the numbers here and I changed the numbers here. Everything else was exactly the same. We'll get back to that. And pretty much every problem on the test was like that. So if you're surprised by anything on the test, it means you didn't go through the reviews. Because I pretty much, when I was writing the test, I went through the reviews and copied the questions. And I changed things here and there, but it was the same questions. Okay. So there was any problem like this on the test. In fact, in version A of our test, it was also exactly problem 7. I was literally going down in the numbers. Oh, problem 7, let me just throw this one on. Okay, but that's another story. There's something else I wanted to point out about this problem. It confused a lot of people. And this was the problem in which I mentioned that I even saw people using the equation for the slope of a line. I see people trying to do y2 minus y1 over x2 minus x1. I'm like, okay, now I know they're really confused. Because that formula does not apply to a quadratic, which starts with an x squared. So then I was like, yeah, they're totally, yeah, there's no hope on this one. But anyway, does anyone actually know how to solve this? Yeah, what did you try?
X into,
Just plug it in.
like plug in X, like given the point,
This point here?
yeah,
Okay.
like
Plug it in where?
into the x squared plus
Okay.
x plus
So
c.
what would your equation look like?
It would be 2 equals to 5 squared plus 5x plus c.
5b plus c.
Yeah, 5b
Okay.
plus c.
All right, so you'll get that equation and then what?
And then you solve, and then you'll, since it's symmetrical to the line x equals to 3,
Yeah.
that
Yeah.
means you have to set it equals, I don't know. Not sure.
Ah, well, that's an issue, right? What does that mean? When we say it was symmetric to x equals 3, what is that telling you? Yeah, Alex.
The vertex, the ax of the vertex is equals to 3.
Right. What the line that a quadratic is symmetric about is actually going to be the line that passes through the x-coordinate for the vertex. It's going to be the vertical line. So them telling you here, symmetric about line x equals 3 is another way of them saying, if you take minus b divided by 2a, 3 is going to be the answer. That's what they're saying. Okay. So now that you have that information, okay, so you have the equation, as she rightly said, you can plug in these points here. You would get 2 equals 25 plus 5b plus c, and you also know that minus b divided by 2a is 3. What do you do now?
So you solve for B.
Yeah?
You do the negative b over 2a, but you plug in, you put 3 on the other side of the equation to find
Right,
b.
yeah, that's what I said. Yeah, but what do you do with that information now?
Now you plug in the b value into the equation.
We don't know the b value.
Solve.
Here we just have b. That's not a 6, right? This is actually the letter b.
Yeah.
Do
We
you,
don't know that value.
since you said negative b over 2a
Yes.
equals to 3, and
Right.
you're trying to solve for the b value, and since in the
How would you
equation,
solve for the b value?
in the equation I had,
Oh, you
I
plug
was,
in the a value.
You plug in the a value. What's the a value?
5.
No, one.
No.
Whoa.
Oh, it's 1.
The a value is 1. The a
Yeah,
is the
one.
coefficient of the x
Yeah.
squared. So basically, them tell you it's symmetric about y equals x equals 3. That's another way of them saying minus b divided by 2a equals 3. You know the value of a because it's going to be the coefficient of x squared, so you plug the a into that. You'd find the b value. Then you can put the b value here, right? And from that you can find the b value, and so now you'll know the a value, you'll know the b value. And the last thing they ask you about is what is the c value? And then you can plug in this coordinate here into there, right? So the 2 goes for the y, the 5 goes for all the x's, and at this point, since we already found the b using the vertex, we can now find the c. C is going to be the only unknown in that equation, right? Now, I wrote the solutions out for our exam. It's already on Blackboard, so you can actually see the entire thing written out. So you don't even have to copy it down what we just said. The point of me going through that is the following. You can look at this single problem that just talks about a quadratic, but do you understand, you kind of appreciate how many concepts you had to go through, and that you kind of had to organize them in a certain order to kind of get from the beginning of the problem to the last part of the problem. One thing what this problem illustrates very nicely is one of the major differences between Math 2009 and the class that you guys just came from, Math 1030, or whatever that number was. Okay? You see in Math 1030, you're never really going to see a problem like that, right? You're going to have a problem where it's just going to tell you, find the vertex, right? And they're going to give you all the values filled in. It's going to find the vertex, find the line this is symmetric to. All the values are filled in, and if you know the formulas, there's no reason why you shouldn't get that answer correct.
Yeah.
This problem, though, was very different. Someone can know all the formulas and still not know how to do this, right? I'm sure everyone in the class knows the formula for a vertex is minus b over 2a. But yet not everyone knew, very few people knew how to use that knowledge in this question. Okay? So that's the first point I wanted to bring up about Math 2009. Knowing the formulas alone is not enough. It's important. You need to know them in order to solve a problem, but it's not enough. Let's go to another problem that illustrates this. That even more so than here. Here we were literally given some numbers that, okay, if you understand the concept, we can, okay, go plug them in, figure it out, go back and forth. You can play this little back and forth where you can get these equations, you know you're chasing down what are the values of b and c, right? But if you scroll down, you can look at problem 21, for example. Now, I didn't put a problem like this on the exam, but could someone answer this problem? It was one of the things you had to look over for the review, but I did put something like this on the exam. Someone else. So it says the equation of the line is shown, y equals ax plus b. Which of the following is always true for this line? A times b is always less than 0. A times b is always greater than 0. A times b will always equal 0. A will always be equal to b, or a will always equal to minus b. Now what do you guys think?
A times b will always be greater than 0.
Always be greater than 0. Okay. What else? Any other? Do you agree, Alex?
I think it's always less than
You think it's always less than 0? Okay.
Yeah.
You agree with less than 0?
Yeah.
Anyone not sure? Yeah?
No, I'm not sure.
You say not sure, okay. Now this problem is different in the sense that there are literally no numbers here, right? Sure, they put some numbers on that, those don't help, they don't even pass through the line, right? There are literally no numbers. This is a problem where it's purely a concept idea. You can know all the equations of the line, you can know, okay, the slope is given by y2 minus y1 over x2 minus x1. It's not going to help you. You can know the equation of the line is mx plus b. Not going to help you here. Okay? And you can look for clues. Maybe they'll tell me the value of an a and b in a secret way. Nope, they're not telling you anything specific about the values of a and b. There is no calculation you can actually do to solve this problem. It's purely a concept problem. It's purely a problem where you have to know about the idea of what it means to be the slope of a line, what it means to be the equation of a line, what these values would actually be. Okay, so Alex, you thought less than 0. Explain your idea. Explain why you believe that.
because in this case, the y-intercept is lower than 0, meaning that it's always going to be a negative number.
Okay, okay, so that's the first concept. He looked at the y-intercept and saw it actually touched the xy plane below the x-axis. This means the b is a negative number. We know that y equals ax plus b. If you write the equation of a line in this way, the b is actually going to be the y-intercept. So he looks at the y-intercept and notices, hey, that's definitely a negative number, right? Regardless of what that number is, we don't care. It's negative whatever it is. So that was the first clue. Okay, b is negative. Okay, then what did you say?
Then I look at how the slope of the line, and
Okay.
this one is going up, so it's increasing. So a is always going to be greater than 0.
Okay.
And that's a positive number.
So again, now he looks at, so he identified the y-intercept as a negative number, and now he's looking at the picture of the line itself. One thing that would jump out at you is it moves up as you go from left to right. This tells you a line is increasing, and this tells you it will have positive slope, which means whatever the number is multiplying the x in the equation of a line, the m, which they write as a here, but it shouldn't confuse you either way, you should know that a is the slope. Whatever that number is, we have no idea, we have no way of knowing exactly what it is from this picture. But whatever it is, it has to be positive, right? And I know it has to be positive because the line is increasing, it's going up as I move from left to right. So you put those two facts together, b has to be negative, no choice there. Don't know the value, but I definitely know it's negative. A has to be positive. Don't know the value, but I know it has to be positive. And I know these because of ideas, what it means to be a y-intercept, what it means to be the slope of a line. How can I look at a picture and kind of talk about how these guys would behave? And so because a is always greater than 0 and b is always less than 0 regardless of the values they're taking, if you multiply them, you have to get something less than 0. So a is actually the answer here. Again, and I've seen, now of course, clearly there are some problems that are direct calculations kind of things. You know, find f of 2, you just know to plug in. F of 2, where would, how, oh, this is another problem I saw out here left. This is a direct computational problem. It requires you to know a concept before, but it's mostly computational. How would you actually do that? F of 2. Yeah.
So you look for 2 in whichever equation on the left,
Okay.
and then
I don't know
it's
what
on
you mean by, what do you mean by look for 2?
where it belongs, like which group it belongs to. So it belongs to the first group because 2 is less than or equal to 3.
So when we say f of 2, the 2 is telling you an x value. So you know the x value you want to plug in is 2. And so you want to know, so here the function is describing 2 definitions for 2 different groups of x's. You can have if your x is less than or equal to 3 or if it's bigger than 3. 2 is not bigger than 3, so you ignore that line and you only look at the first line. 2 is less than or equal to 3, which means that this is the definition of the function, and all you have to do is plug in 2 here, right? And you get minus 7 as the answer. Okay? So it's just, you have a little bit of a concept preceding it. You just have to know, I need to ignore certain information. Remember that a function will always have one output, so you'll never get a list of numbers as the answer. So you just have to know the idea of where to plug in the 2. Okay. But clearly, that's very computational, and you have a lot of ones here that are very computational. But the idea is, you will always have questions like this. And even ones that are very computational, you will always have a lot of questions like this, where even though it's mostly computational, the amount of ideas you have to go through to understand where the calculations have to come in, where you have to plug in the numbers, what you have to set things equal to, is a lot, right? And I just want to emphasize, it's not enough to just know the formula or to just know these things. You have to know when a formula applies. You don't just need to know, oh, x equals minus b over 2a gives me the vertex. You need to understand that also tells me about the symmetry of a quadratic. It also tells me about where a quadratic will hit its highest point and its lowest point. You have to know the idea of what it means to be the vertex, what this can tell us about a graph. Okay? So just knowing the equation isn't enough. Okay? Now, the point of me saying that is the following. Or me pointing that out. A lot of you have come from 1023, and you've gotten into a certain way of doing things, a certain way of thinking about problems. And you might come to this class and might feel a little bit disillusioned, right? You might think, for example, that, Javon's making things harder than it has to be. I don't understand why he's teaching me this way. Back in 1023, the instructor just came and gave us the formula, we did problems, and everything was fine. We went home. And, I just went home and I studied the formulas and I practiced and everything was fine. I don't understand why Javon is making it so difficult, right? Why is his quizzes like that? Why are they so confusing? And you might complain. And some of you might actually even be studying very hard. You might actually be working hard and not complaining. And you're still just not making a grade and you're not understanding. And what is happening there, more than likely, is illustrated by the problems I just showed you. 1030 and 2009 are different animals. They're not the same kind of course. They're not the same kind of math course. The same kind of studying will not work on both. So you might have gotten an A in 1030. You might have done very well, right? But if you take exactly those same study habits that got you an A in 1030 and do it in 2009, you're not going to get an A. It's just not going to happen, right? You'll probably pass, right? If you're an A student in 1030, you probably have some concepts internalized that you don't even realize you're applying. But you're not going to do as well. It's a very different animal, and knowing what you have to prepare for is important. It's one of the reasons why I told you guys, actually go through the review, time yourselves while doing it, so you don't end up in a time issue, which a lot of you did, right? So you can have an idea of what is actually required, what you might need to know. And some of you might have done a few problems on the review, some of you might have looked over your notes, practiced a problem here or there, maybe looked through some worked out examples, but there are things you probably weren't paying attention to. And those things I tell you, so for example, I do a problem where I'm working out an example, and you'll notice that while I'm working it out, I'll go over here and I'll write some notes in a different color pen or things like that. And what you need to realize is that it's because I realize that this exam requires you to know concepts as well as the math behind it, right? You need to know the ideas. So if you just go through your notes and you literally just, okay, let me look at the formulas, let me see how Javon worked this out, it's probably not going to go well for you. You need to understand the ideas. You need to understand, why did Javon do this? Why did he do it? And I always tell you, I always go to the side and I write out the notes, right? Those little notes to the side, they're just as important for you to study as the formulas themselves, right? How you study is going to be different in this class than it is from 1030, okay? So it's not that I'm making things harder than they have to be, or it's not just that you have bad luck or maybe you're bad at math. It's quite possible you're studying for the wrong class, right? That is a very possible issue, okay? Now there are some of you who don't even know the formulas. Let's make that clear. Like why would you do y2 minus y1 over x2 minus x1 for a quadratic? That's a different story. But a lot of you, I think, you're studying for the wrong course. And you need to be aware of what you're up against, right? And you need to be aware of things like, well, I don't know what a phrase is in general, but in like with sports or fitness, they call it specificity of training, right? So it means like if you want to be good at doing something, you have to practice that thing, right? Practicing other things to kind of think there's going to be some carryover to the thing you want to be good at, it does not work, right? If you want to practice running a sprint, a 100-meter sprint in the fastest time possible, you'll have to practice running 100-meter sprints. You can't practice sprinting for 50 meters. You can't decide to run a marathon, or you can't decide to do go to the gym and do squats, and you can't decide to do lunges and run up and down stairs. If you want to be good at sprinting 100 meters, you have to sprint 100 meters regularly. That's just how it works. That's how your body adapts, your brain adapts. It's just how it works. To be good at something, you have to do the thing, right? And so when I told you guys, make sure you go through all the reviews. On one hand, the test would be a lot less surprising because, as I said, pretty much every problem. There were probably 2 problems on the entire exam that didn't directly come from the past finals, but they came from the final that my class last semester took, so I thought it would be good practice with something more recent. But pretty much every other problem is I went through the review, the same review I told you guys to go through, and I just changed the numbers, maybe changed the story. Or something said, a person did this, I wrote in Bob the Builder did this. Like just silly things to kind of make it look different, but it wasn't any different. If you went through the review and you went through it how I asked you to go through it, the test shouldn't have been a problem. But it's also worth pointing out that maybe you did go through the review, but you kind of focused on the formulas or the calculations that you should know, rather than focused on the ideas and the concepts you should know and how they tie together, right? So 2009 it's a different course. You have to appreciate that it has to be taught differently and it has to be studied differently, right? So you want to avoid having this disconnect, okay? And that's going to cause you a lot of trouble, you know? And it's kind of like, you know, famous quote, very overused, but you know, from the Art of War by Sun Tzu, and he said, if you go into battle and you know yourself but you don't know your enemy, right? Then every battle you win, you'll also lose one, right? If you know yourself, if you don't know yourself, you know your enemy. If you don't know either of those things, then you're going to lose every battle, right? You kind of have to understand both where you stand as a student, and you need to understand where the class you're preparing for is. You need to understand yourself, you need to understand the class. So you need to understand 2009 as a class is different from 1030. It's different from 1030 in that the concepts are important. So you pay attention to concepts. You have to understand yourself, and understanding yourself is the instructions that I tell you to do. Do the tests under timed conditions. Don't do it while you're watching TV. Don't do it one at a time. No, do every problem on a test in one sitting under timed conditions. This is a part of knowing yourself. Doing that would have told you that, hey, I'm going to have a time issue by the time I get to this second part of this exam, right? You would know that before coming into the exam, and you wouldn't have run out of time. You'd understand yourself, okay, I'm slower here, I'm faster here, I'm good with this, I'm not so good with this. I need to organize my time better to make sure that I come out with the best possible outcome. thing. The specificity of training is very important. Okay, this is why if you go and you pay a lot of money for courses that are supposed to prepare you for the SAT or the GRE or any standardized exam, a lot of that time, you might have noticed, anyone who has taken that course, a lot of that time, you're just sitting in a room and they're watching you take a test. Right? If you come over here, you're going to pay me money to sit in a room and I'm going to give you a test. And we'll go over it afterwards, but it's important that you realize they always make you do tests because they're preparing you for a test. If you want to prepare for a test, you have to practice doing tests. That's how it is. Kind of looking through your notes, memorizing the formulas. That's good, but it's not going to be great. You know. In the same way, if you always practice running marathons, sure, you might be decent at sprinting 100 meters. You're not going to be great. You're not going to be the best. You're not going to get the A. You're not going to get the gold. Right? The person who practiced sprinting the 100 meters is going to get the gold. So this is all very important. And in terms of when you're at home or when you're with a tutor, you have to understand that these are important things for you to consider, important things for you to worry about. So even if you're with a tutor, you have to make sure that you're being as productive as possible. Even when you're in recitation, you have to make sure it's as productive as possible. You have to know the questions you need to ask. It's not just a matter of, oh, what formula I should use here. It's, why should I use that formula here? Okay, if we have to use two formulas for this, you use this one first and that one second. Why did you have to go in that order? What was the concept? What in the question hinted to you that this would be the thing? What is the idea? What are other ways I can interpret this formula? Okay, you give me the formula x equals minus b over 2a. Tell me in words what that means. What would it indicate? What does it tell me about a quadratic? And then you'll get the answers of, oh, whenever they mention symmetry with a quadratic, that's the vertex, right? That's another way of saying the vertex formula, right? They mention the maximum or minimum of a quadratic. That's another way of saying you need to use the vertex formula, right? So just knowing the formula isn't enough. You have to know the concepts and ideas that are surround the formula and when it would be appropriate to use the formula. Okay? So there's another dimension to studying for this than there is to 1030. And it's important that when you're studying whatever you're doing, you always have that in mind. You always need to know yourself, your own strengths and weaknesses. You also need to know the nature of the beast you're preparing to conquer. You need to know what it's like. If you're preparing to kill something else, it's not going to go well for you over here. How you prepare to fight a kid in class is not the same way you prepare to fight Mike Tyson. That's a different level. These are two different things, right? You want to hire a professional coach to fight Mike Tyson. Probably give yourself a very long time to train and build up. Whereas some kid in class, whatever, I can get away with being a little sloppy. So I just wanted to point that out. That's going to be very important, not only in how you pay attention in class, what you pay attention to in class, and the questions that you ask in class. It's also going to be important that when you're studying at home, how to actually know you really get it. You know what I mean? And you're not surprised on a test. And you don't run out of time, or you just get stuck and you don't know where to look or what to do. Right? So the concepts are very important in 2009, far more important than they were in 1030. And that needs to be appreciated. Until you appreciate that, it's going to be a rough time. And until you actually start practicing for the way you want to perform, you're going to have a rough time. So I just wanted to point that out. I had a couple of students when I was just like going through my test and I was pointing out, okay, you see this problem on my test? Look at this problem over here on the sample final. Okay, see this problem? Look at that, look at that, look at that. Oh, whoa, this is really the same. It happens every semester. I see a bunch of students who just didn't realize because they never put the practice. They never decided, let me practice specifically before taking this test by doing all the tests. Okay. So, and again, as I've mentioned this before, which I know it's hard for students to have that trust. I understand that a lot of you might have had teachers that have hurt you before, but really, I want you to do well. If I tell you that, hey, you should do this, I really mean you should do this for your own good. I'm not going to tell you something that's not important or tell you something that's just going to waste your time. If I say, hey, you need to go through this process to prepare for this, I really mean you need to go through this process to prepare for this. That will prepare you the best way possible. You need to look at things in this way. You need to pay attention when I say you need to look at things in this way. That will prepare you the best way possible. If you kind of go off and do your own thing, or you kind of go off and did things the way you did it before, it's not going to end well. Now, I think that was important to say because that would kind of make your study time and your recitation time more important. I'm not here during the recitation. I wish I was, because it's very important that you guys, I want to know that you guys are actually asking Aaliyah the right questions and you're actually participating in the recitation, because you need to understand what you need to know and at what level you need to know it. And so if Aaliyah just solves a problem and writes down a formula and you just copy it in your notes and go about your business, you're doing it wrong. Why did you use that formula? What about the problem tells you that you had to use that formula? Can you rephrase this question in another way that might show up on a test that they'll try to trick me, but I should know I should use this formula? Right? These are the questions you should be asking her. You should be really playing around with the ideas, playing around with the concepts, playing around with the formulas, trying to understand them from different angles, trying to understand what words in English might indicate certain formulas. And of course, actually knowing the formulas well enough to know some apply to this, but they don't apply to other things. Okay? So in general, if you want to find the max or min of a quadratic, yeah, you can use x equals minus b over 2a. If you want to find the max or min of anything else, that does not apply anymore. Minus b over 2a doesn't apply to anything other than a quadratic. Things like that you need to know. Right? These are the questions you need to ask. Right? Is this formula always how I would do something like this? And then they'd explain, well, no, this will work for a quadratic, it won't work for this, and then that's a concept that you should now be aware of. Okay, there's a concept, you need to write that down, you need to circle that. It's just as important as knowing the formula. Now, we started with another concept last time, the concept of what a limit is, and we're going to continue that now. And we are going to make that a little bit more concrete. I started by showing you a lot of examples with pictures because you'll notice, when you start reviewing for the next test, you'll notice that a lot of times they ask you a question in terms of a picture. They'll give you a picture and say, hey, what's the limit as we approach here? So it's very important that you understand the geometric idea, but it's also important that you actually know how to actually compute these guys as well, and the concepts as they would apply. So last time we started talking about limits, what a limit was. So recall, so the limit means, and this is what I'm talking about as a concept. And I know a lot of people are confused about limits the first time they see it because it is really more of a concept than a formula. There is no formula to always compute this. It depends on a case-by-case basis purely. This is the kind of problem you solve by knowing the concept, right? So whenever you see that expression, right, what it means is that as x gets close to a, the y values, right? And by y values I mean the f of x gets close to a unique value L, right? So that's an idea. This is what it means as a concept. There is no formula, no general formula for this expression. It's an idea, right? And it's also very important that you pay attention to how the idea is described. It's described in terms of getting close, which means you don't care about being at the point. You don't care whether the function is defined there, or if there's a hole, or there's a gap. These are not concerns of yours, right? Because you don't need to actually be there. You just need to get close, right? And that's the idea, right? So as your x is getting close to this number, your y values will get close to that number. And so we saw examples like, if I said limit as x approaches 1 of 2x plus 1, this was 3. Because as your x values get close to 1, there's only one number that this expression will get close to, and that is the number 3. And you could see this from the picture. 2x plus 1 would look like that, and here's your 1. Here's a point on the graph which is floating around 3. Now again, I don't care about actually being at that point. I just care about if I get closer and closer to 1, the y values are getting closer and closer to 3. And this happens in a unique way, meaning if I go from the other side, the y values will decrease until they are starting to converge at 3, right? So zoning in on 1 causes the y values to zoom in on 3. Okay? Now, you could have a hole here or a gap here. It is irrelevant. Whether a circle is shaded or not, whether the function exists or not, is irrelevant when it comes to the limit. Because we don't care about being there, we care about getting close. And it's an idea. It's a very intuitive idea. So we can make a statement like that, right? And we also saw that it also breaks when you don't have a unique value. So we actually looked at a function that looks similar to something like this. I believe this was also at 1, this was at 1, and that was at 3. And we could say that the limit as x approaches 1 of f of x here does not exist. And the reason is, if we're getting close to 1, there is no unique y value that we approach, right? There are actually two y values that we approach. If you come close to 1 from the left side, all your y coordinates here are going to be outputting 1 or something close to it. Whereas if you get close to 1 from the right side, all your y coordinates here are going to be getting closer to 3. So is it 1 or is it 3? That ambiguity breaks what the limit does, right? The limit is looking for a unique y value. The fact that there are two possibilities means the limit does not exist. And this idea, though, was a little bit unsatisfying, so we talked about the one-sided limits. We're still in the recap, where I'm not saying anything new at this point. We could talk about a limit as you approach that number from the left, and we would put a little minus sign in the superscript here. And this is from the left. So there's a difference when someone just says x is approaching a number versus x is approaching a number to a negative sign, right? That just means you're literally ignoring the right side and you're only looking at the left side, getting close to 1 from the left. Means your x values are a little bit less than 1 and they're slowly increasing towards 1. And then you look at what the y coordinates are doing on the function. And in this case, they would have hit 1. That would actually give us an answer. And we can talk about the other side, limit as x approaches 1 from the positive, right? And this means from the right. Meaning in this case, you're going to ignore the left side of the graph and only focus on what's going on the right side. So as x is a little bit bigger than 1 and inching down to 1, we would be on this side of the function. That's where our x coordinates are larger than 1 and getting closer. And the y coordinates will get closer to 3. And so I can say this was 3. And then we also spoke about, okay, in order for this definition to work, another way we can put that all together is to look at the one-sided guys. And if these guys both give us an answer, and it's a different answer, we'll say the limit does not exist. If they both give us an answer and it's the same answer, we'll say the limit exists and it is that number. And so this led to the existence of limits. And the idea is this guy only exists if both coming from the left and coming from the right exist and they're equal. And then the limit as x approaches a of f of x will equal the same value. And I think that's kind of where we ended up last time. We did a few more examples, but those were the main ideas we introduced at the end of the last class. Okay? So limit is tracking the y values. You want to talk about the behavior of the function as the x value is manipulated in some way. So you're trying to get the x value close to some other value, and you're trying to see how do the y values respond? What do they get close to? Right? And this must be a unique value, meaning if you get close to two separate values, limit does not exist. We can talk about one side at a time, and those individually can exist. They might also not exist. Maybe we might do some examples of that. I think those rarely come up though. But it's possible for even the one-sided ones not to exist. But provided these two exist, they must give you the same value in order for the overall one to exist. And that is summarized by this idea here. So that's where we were. We're going to make use of limits a lot. Last time I told you that the main tools of calculus are actually written in terms of limits, so they're very important tools to understand. So now that kind of brings us to actually computing them. So every now and then you will be given a limit of an expression like this, and you want to know, how would I calculate this without having to worry about what the graph looks like or this or that? Even though a lot of times the graph is going to be the way you're going to do it. But there's a way to actually computationally figure these guys out. And we did some of that last time, even though I didn't emphasize it, we're going to do more of that today. So knowing what a limit is from a picture should be something you're comfortable with. It will come up in tests and on the final. It's very common. But now we're going to also look at other ways that limit problems can come up, and that's in terms of the computational ways. And I'm going to tell you the strategy, how you would approach any limit problem, as well as a very common scenario that you'll see, and how to deal with it very easily, in fact. Then we'll move on to continuity, which was in the bonus of the quiz today. So let's actually move on to the idea of computing limits. So if I ask you a limit, I don't give you a picture. Find this limit. What do you actually do to figure out what that limit actually is? So this is just the computing limits. First thing you should know about computing limits, limits do have certain properties. Let's look at their properties. And usually when you talk about properties of something, it's talking about the algebraic properties. Meaning, how does this concept behave with arithmetic? So it's very important that you know these properties. So here we can say, suppose C is a constant, and limit as x approaches a of f of x, limit as x approaches a of g of x, exist and are finite. Last time we saw examples where the limit can be infinity, but we're assuming here these are finite. They will give us actual numbers if we compute them. Then there's some important properties that you can look at to know how to actually compute a limit. For example, the first property tells us that we can actually factor constants out. So let's say I know the limit of f and I know the limit of g. What is the limit of c times f? It turns out that you'll actually be able to factor this guy out and multiply by the limit of f. So let's say this was L and this was M. This guy would be c times L. That would be the number that you would get as a result. How about example? We know the limit of this guy is 3. It would also mean that if I were to look at this guy, 5 times that it would just be 5 times 3. If you're multiplying a function by a constant and you want to take the limit, the result is just going to be the constant times the value of the limit. So this is the 5 times 3, kind of like the C times L. Okay, so that's one property. Okay. So if you already know about a limit, you automatically know about any constant times that limit. Second property. Limits actually distribute across sums. So if I have the limit of f of x plus or minus g of x, then there's a distributive law that the limits will actually obey. You can actually split the limits up and do them individually. So limits actually distribute across sums. So if I have two things being added together and I want to find the limit, I can just take the limit of one at a time and then add the answers together. So, example, we know that the limit as x approaches 1 of the 2x plus 1 equals 3, and we also saw the limit as x approaches 1 of x over minus 1 over x minus 1 was, I believe that was 2. We did an example like that last time. Okay, so we know that. It means, therefore, that if someone were to ask you, what is the limit of 2x plus 1 plus x squared minus 1 over x minus 1, the answer is simply going to be 3 plus 2. You're going to find the limit of this part, find the limit of that part, and add them together. Right? Limits distribute across sums. So you can actually just find the limit of one at a time. I can just take the limit, find the limit of that, then take the limit, find the limit of that. I'll use two different strategies for each one of these. We'll talk about strategies in general later. But once I know the individual limits, I automatically know the sum of any two limits. I'll just add those guys together. So limits distribute across sums. The answer here would be 5. Three. Limits are some of the nicest objects you'll see in this class and pretty much in any math class because they actually obey a lot of the rules that you want them to obey. They distribute across sums. They also distribute across multiplication. So if you have f of x times your g of x, you can actually take the limit of each one separately and multiply them. Now that's super special. Not a lot of things do that, right? For example, we know that powers distribute across products, but they don't across sums. Remember, that's a last week, right? So if you talk about the process of raising something to a power, it doesn't obey both of these. It only obeys one, right? Limits actually obey both of these. It's very nice in that regard. There's a lot of things that it distributes across a bunch of things, both addition and multiplication and division. Limits actually also distribute across division. As long as you make sure that you avoid division by 0, everything will be fine. So if you see a limit like that, it's just going to be the limit of the top divided by the limit of the bottom, provided the limit of the bottom is not 0. So you can factor constants out. Limits distribute across sums, they distribute across products, they distribute across division. So limits are actually very nice. You have to just be aware that it has these properties. You also need to be aware of things that don't have these properties. Not everything will have all these rules. Right? We'll see that in even the next few sections, other objects that they can also go inside powers. So if I want to find the limit as x to the a of fx raised to some power, I can actually just focus the limit on the inside and then raise the answer to the power. This rule is usually stated that n is a positive number. That's because you don't want the case where n is negative and now it goes into the denominator, and maybe you could divide by 0. But the idea would be the same. So limits are very nice. In fact, limits kind of pass through any function that is continuous. We'll talk about what that means soon. But yeah, those are some 5 properties that we can talk about right now. So limits are very nice algebraically. They work kind of in the natural way that students want things to work out in all the time. Right? They distribute across everything. It's basically the idea. Limits are very nice in that regard. So computationally, you kind of have a nice time with limits here. So the actual computations usually will never be that hard. What students tend to find hard is that the idea of a limit scares them, so once they see that symbol, they would freak out. But actually, computationally, limits are actually very nice. They work with almost everything across almost any arithmetic operation. So that's very nice here. Good. So we'll talk more about that when we get to some examples later. But let's now talk about the strategy. So there are a bunch of times where you're going to be asked to actually compute a limit. So I'll say, compute this limit, right? So the a is going to be some number, maybe it's from the left or from the right, and the f of x is going to be some function. It might be described by a graph, but it also might be described by a form. And so if you're faced with a random limit, right, just out of nowhere, oh, find this limit, how do you actually go about doing it, right? So I want to give you like a general strategy, a general approach for it, kind of like what we did to factor with factoring. If you want to factor something, first look for the GCF, then look for this, then look for that. I want to do the same kind of thing here for limits. Okay? Kind of narrow it down and kind of give you a sort of actionable strategy to computing these problems. So, step 1 when computing a limit. Try to plug in. Now, that is if f of x, I kind of want you to remember the phrase try to plug in. Let me just explain what I mean. If f of x is defined at a, then plug in a into f of x. So try to plug in would be the first strategy. That's always going to be the first thing you want to try. Okay? Now again, limits don't care about being at the point, but if the point does exist on the function, you can't get closer to a point than actually being the point. So here you can kind of get away with something if your function is continuous. So for example, our very first example was something like this, right? And we looked at the picture on the graph and tried to understand why the answer was 3, what it meant for the answer to be 3. But computationally, it could be a lot easier. Because this function, 2x plus 1, is a polynomial. The domain is all real numbers. It works for every x value that you can plug in on the number line. So you can actually plug in the number into that function. You could literally just plug in the 1. So the answer would be 3. Now, again, this doesn't always work, right? And the limit doesn't care about being at the value. It doesn't care about being 1. It cares about getting close to 1. But whenever it's possible to plug in the number, that's as close as you can get. That's pretty much, that's it. You just plug in the number, and that's going to be your answer. So if you're faced with a random limit, step 1, the first thing you're going to look for, could I just plug this in? And if you can, that would be fine. That's actually the answer. There's nothing else to do. However, it's not all the time that you can actually plug a number in.
Cancel.
Okay?
It's a factor here. You have to enter. And then you have to plug
Okay, so if I give you a random limit, the first thing you're gonna do, always the first thing you try to do is plug in the number. If you plug it in and it works, great. You just move on with your life. There's nothing else to do. Sometimes that doesn't work though, and so if 1 doesn't work, plugging in is still a very nice thing to do, so you try to salvage it. Try to simplify so you can plug in. So our second example kind of embodied this principle. I asked you, what is that limit? And again, we looked at the graph last time and tried to figure that out. But the idea here, you'll realize, is that you actually can't plug in x equals 1, at least not right away. Because if you plug in x equals 1, you actually divide by 0. So that can't be done. So we can't really follow step 1 here as written. So the next step, once you realize I can't plug in, you don't just give up on the whole plugging in idea. You immediately think, can I simplify the plug in? I'll simplify. Now here's where your algebra skills come into play. So you need to be able to look at an expression. You need to be able to recognize that it can be simplified. And then you need to be able to simplify it, right? That's algebra skills. Okay. So for this one, it's not so bad. Hopefully you realize it's not so bad. How do you simplify that?
You factor the top.
Factor the top, right? And again, that's a general principle.
You cancel x minus 1.
So let me just stop there for a second. That's a general principle. You have a fraction and you want to simplify it, always factor. Factor the top, you factor the bottom, and cancel. That's what it means to simplify. That's an idea. Okay. Now, so yeah, so you can't plug in, then you ask yourself, could I simplify this in a way to plug in? And so, yeah, you realize, okay, the top is a difference of squares. I can factor that, and then, as she said, you can cancel. So now what you're looking at is this expression. And also now, you're in a situation that looks kind of like this one. If you look at x plus 1, there's no problem with plugging in x equals 1 at this point. So you would just do it. And the answer here is 2. So that's the next scenario, that's the next level, right? So a super easy limit problem is one where you can just plug in a number, right? Then one that's slightly harder is one that you have to simplify to be able to plug in the number. But it can get a little more sticky than that. Sometimes you can't plug in a number and you can't simplify. How would you deal with that situation? We're going to do a few examples. You can also redo the examples that we did last class. When we did it with pictures, you can actually redo it using these strategies to kind of get some extra practice here. So 3. 2 doesn't work. Now here is where you are going to try to look for a special technique. I think for this class, There are a lot of them, but for this class, you kind of only need to know one. So I'm going to tell you about that after, but it'll probably be this thing we need to know. One. So that's going to be limits at infinity of rational functions. So that's a very special situation that can show up. Whenever that situation presents itself, it has its own strategy for how to construct it, but it's probably going to be the thing you want to look at next. Is there a special strategy? Does this fall into a form that I know how to manipulate, other than by doing something like this? This brings us to 4. 3 doesn't work. Look at graphs or plug in numbers closer and closer. Okay. So this requires you to have graphing skills. So you should be able to see a function and know what its picture looks like. Now we've been doing that for a while. I've asked you on quizzes to graph things all the time. So hopefully by the time you get here, that should be no problem. But one of the quickest ways, compared to these two, graphing would usually be easier than plugging in numbers, because you have to actually do some arithmetic there, and that might take some time. So graphing would be probably the better one. So an example of something that would apply here, we had 2 that we looked at last time. Look at x approaches 0 minus of 1 over x versus x approaches 0 of 1 over x squared. Now, if you saw this guy, right, that was the problem that was presented to you. First thing you would try to do, plug in x equals 0. Then you're like, oh, I can't do that. So second thing you try to do, can I simplify to plug in 0? In order to simplify this to plug in 0, you'd have to be able to cancel the x, but look at the numerator, it's 1. You'd never be able to cancel the denominator, so you can't simplify either, right? The special technique that I'm going to teach you does not apply here, so we can't do that, unfortunately. So now we're kind of stuck in this area. Okay, how do we figure it out now? Well, a graph is going to be a very nice way to do that, very easily. Just remember what the graph of 1 over x looks like, which I assume everyone knows by now. It's that. Okay. And then you kind of examine it from the picture based on what we were doing last time. You'll notice that here, as x is approaching 0 from the right side, the y is approaching infinity. So we're getting close to 0, our graph is shooting up. So it's going off to infinity. And over here, we look as x is getting close to 0 from the left side, the graph is going down. The y is approaching negative infinity. Then you realize that, hey, not the same. And that implies this guy does not exist. Now if you look at this example, now just because you can't simplify or plug in or anything like that doesn't mean it does not exist. It could just mean it's also infinite or behaves in a strange way. So the graph of this 1 over x squared, you should know it looks like that. And now you can, again, one side at a time. As I approach 0 from the right side, my y value goes to infinity. Coming from the right side, as I get close to 0, the y coordinates are shooting up. Coming from the left side, as I get close to 0, the y coordinates are also shooting up. So if I go x from negative, and y is also infinity. Then I would make the astute observation that these are the same. And that would mean that I'm going to fill in that as the answer. So given a random limit problem, step 1, try to plug in the number. If you can plug it in and get an answer, great, that's the answer. Move on with your life. Step 2, if you can't plug in the number, try to see, can you simplify to plug in the number? Is there some sort of algebra trick you can use to plug in the number? And this might be factoring, combining fractions, whatever. Any algebra trick that we've looked at in chapter 1, in simplifying things or solving equations are game here. They will apply. You need to remember everything. Remember all your algebra skills. Okay. Now, sometimes even that can't work. Sometimes because it's kind of difficult to see how it will work out, but sometimes because it literally can't, right? So in this case, I couldn't plug in x equals 0, and I couldn't simplify it to be able to plug in x equals 0. I had very little choice here. So at this point, I'm going to start looking at the graphs. Now, sometimes the thing you have, you might not want to graph it, maybe you forgot what the graph would look like, and so there's also the plugging in numbers option. Let me show you how that option would work. And again, I'm going to compare the two. I'm going to compare an example when it does not exist to an example when it does exist, and for you to see the difference. So if you look at this guy, 1 over x versus this guy, 1 over x squared. Okay. What I mean is plug in numbers is to create a table of values. And I want you to remember the definition of a limit. It talks about getting close. You want to real emphasis on getting close here. Okay? So the numbers you're going to plug in aren't just some random numbers. They need to be really close to the number that you care about. So, for example, if we're looking at this guy, I can have x values, and I'll see what the 1 over x is doing. Now, ultimately, I want to be able to talk about when x gets close to 0, what's going on over here, right? That's the question you need to answer, right? Now, in the beginning, you don't know this, but what you can do is you just literally inch close to it via some calculations, okay? So let's say, okay, I can start at 0.1, 0.01, 0.001, 0.0001. Right? Very close to 0, okay? Start off at like 0.1 or 0.01, right? You don't want to start off at like 1 or 5 or 17. Those are too far away. You need to be super close to 0, a very small number, and then you start making it smaller, inching it towards the target, okay? So you really want to emphasize close here. You should only be like a few decimal points away, okay? And then you just make it smaller and smaller, sort of inch close to 0, and now you're going to watch the behavior of what's happening over here. So, of course, 0.1 just means 1 over 10, so if I plug that into 1 over x, it's going to flip it, it's going to become 10. This one is going to become 100. This one is going to become 1,000. This one is going to become 10,000. You'll notice a pattern that's happening here. Hey, these numbers are getting bigger and bigger and bigger. Now, when a bunch of numbers just keep getting bigger, there seems to be no end in sight. You can, of course, imagine, had you put 4 zeros here, the number gets even bigger. That tells you it's approaching infinity. The numbers just keep getting bigger. And if I get closer to 0, they're going to keep getting bigger. You can play the same game, and so you understand that a limit has to behave both the same on the right and the left. So here's where you're looking at what's happening from the right. Okay. So from the right, let x, so means x is a little bit larger than 0, but you're making it closer to 0. And then you're watching how the y values react, because that's what a limit is. As x is getting close to something, what is the y getting close to? That's the whole concept of a limit. So now you just watch these numbers. Are they getting close to anything? No, they just keep getting bigger and bigger and bigger. That's another way of saying, no, it's going off to infinity. You're going to do the same thing down here, right? With the other side. So from the left. Okay. You're gonna start a little ways off, so maybe like minus 0.1, minus 0.01, minus 0.001, minus 0.0001, minus 0.00001. Okay? So this is minus 1 over 10, minus 1 over 100, minus 1 over 1,000, etc. Notice that the y value here is going to give you negative 10, negative 100, negative 1,000, negative 10,000, negative 100,000. These numbers seems to be getting smaller and smaller and smaller. They're getting more and more negative, and there seems to be no end in sight. They're not settling anywhere. So these guys are going here. They're getting smaller and smaller. Smaller and smaller in the sense that these are moving to the left on the number line. This means it's approaching negative infinity. It's just becoming a negative number that's very large in magnitude. And at that point, you're going to notice that, oh, if I'm looking at it from the right and I'm looking at it from the left, not the same. And so therefore, you're able to tell it does not exist. And again, we could do a similar thing over here. Let my x value get close to 0. I want to know what my y values are doing. So let me track what the y value is doing. So again, 0.1, 0.01, 0.001, 0.0001. And this one actually grows a lot faster because it's squaring. So this is 1 over 10. It's going to flip it and then square it. So that's going to be 100. And that's going to be 10,000. That's going to be like 1,000,000. And that's going to be like 100 million. So yeah, those are also getting larger and larger and larger. So you realize here, these guys are approaching infinity. Doing it from the opposite way, minus 0.1, minus 0.01, minus 0.001, minus 0.0001, minus 0.001. Now, the thing with this one is that it squares the value. So it plugs it in, it squares this, which gets rid of the negative sign, and then it flips it. And so you get a positive number resulting again. So this is positive 100, positive 10,000, positive 500,000, positive 500,000, etc. Right? Again, you see the idea here. This side is also going off to positive infinity. You look at this, okay, this and this, they are the same. And so that means you're going to write that down as the answer. Any questions on this idea? So not always is limits going to be given to you as a picture as it was on the quiz. Sometimes they're going to write down a formula. They're going to tell you, find this limit. And there's a process that you go through. First step, can I plug in the number? Second step, can I simplify to plug in the number? Third step, does a special technique apply here? Fourth step, what does the graph look like? Or, if I don't know what the graph looks like, plug in some numbers, figure out what the y values are doing that way. The steps are important. They're just as important as the examples. You need to know the step, you need to memorize them, you need to memorize in a certain order. Always go through this order. That's the idea of how you compute a limit. Okay? So it shouldn't be the case where you go on a test and you see a limit and you're like, I don't know what to do. You know what to do. Step 1, try to plug in. Step 2, simplify to plug in. Step 3, right? You should never be in a situation where I kind of don't know what to do. It's not a thing. You know what to do. You memorize these steps. These are the steps that you do. You see limit, go through these steps. Another idea I want to introduce is infinite limits and limits at infinity. And then maybe you can take a break and I'll show you the special techniques of that. Consider the limit as x approaches a of f of x equals L. Here are the two definitions. If L, right, like the result is plus or minus infinity, for example, as it was in this case, the limit actually approaches infinity, then the above is called an infinite limit. If the a value is plus or minus infinity, that's actually a thing you can actually consider, then the above is called a limit at infinity. So you're taking a limit at infinity as your x value approaches infinity. An example of that would be limit as x approaches infinity of, say, 1 over x. What do you think that would be?
Infinite limit. Oh.
No, as in the answer.
Does not.
Infinite limit.
Does not.
Zero?
Think about it, what would that be?
Limit at infinity.
That's the name, I'm asking you the answer, the answer.
Infinity.
This is the limit at infinity. What is the answer?
It's not.
Infinity. Oh wait, no, it's
Does not. There is no answer.
Go through the steps. What is the first thing you would try to do? Plug in a number. Infinity is not a number, so that's out of the question. Second thing, can we simplify this to make sense of plugging in a number? No, infinity is not a number. Third thing, what does the graph look like? It's like this. As your x is going off to infinity, right? What is the y value doing?
Outgoing.
The graph keeps doing this, right? What are the y coordinates doing?
Going up and down.
As we move to the right, as x is going to infinity,
All of
what is the y coordinates doing?
like getting bigger.
Closer to zero?
It's getting closer to 0. Notice that all these points here, the y coordinate, if I look across at the y coordinate, it's close to 0. They'll never actually hit 0, but we don't care. 0 would be the answer. Not infinite. That's what I mean. I give you a random thing. What do you do? You go through the steps. Can I plug in? No. Can I simplify the plug in? No. Okay, what does the graph look like? Right? You should be thinking these steps. And then once, okay, here's what the graph is doing. As I'm going off to infinity, as my x value gets larger, meaning I'm looking on the number line, I'm looking far to the right, what is the y value doing? If I plot coordinates on this thing, what would the y coordinates be telling me? They'll be telling me numbers successively closer and closer to 0. So 0 would be the answer. So this is an example of a limit at infinity. This is an example of an infinite limit. Of course you can be both. So you can have your x's going to infinity, and the thing also goes off to infinity. So you can be both. Example, silly example. Limit as x approaches infinity of the function x. That's going to be infinity. How do I know that's infinity? Well, try to plug in the number. Infinity is not a number, can't plug it in. Okay. Simplify to plug in a number. Infinity is not a number, can't plug it in. Okay, what does the graph look like? Y equals x looks like that. Okay, what happens as my x values get huge? The graph keeps going up. What does that mean for the y coordinates? They keep getting bigger. Infinity is the answer. Okay? That's the thought process you should be going through. Okay? You guys like, can I plug in? No, no. Can I simplify? No. Okay, what does the graph look like? Right? Ask yourself these questions and then answer them. Talk to yourself and answer the questions. So that would be an example. I'll throw up some more examples, but we'll take a break before actually doing them. You can just start thinking about them. So A. If your f of x equals this, I want you to find A part 1, limit as x approaches 1 of the function. 2, limit as x approaches 0 of the function. Part 3, limit as x approaches 3 of the function. D. What is the limit of x plus 1 squared minus x? C. What is the limit? The square root of 4 plus x minus 2 over x. What is the limit? So we'll take a break. You can think about how you want to answer those, but we'll answer that after the break. So 15 minutes there is. Stretch your legs, wash your face, get something to drink.